So I'm very happy to introduce Sushmita Venugopalan from IMSC Chennai, who will talk about tropical Fukaya algebras. Sushmita was supposed to be with us, visiting us, but in the end it was not possible. But I'm still very happy that you're giving this talk here. So there you go.
Thanks a lot for the invitation. I'll go for 1 hour, right? We're starting some 9 minutes late, so.
Yes,
okay,
yes.
okay, thanks. Okay, so the topic of my talk is tropical Fukaya algebras, and it's based on a joint paper with Chris Woodward, which is on arXiv. So I start by introducing my problem. So I start by telling you what a symplectic cut is, which might be familiar, but still worth reviewing. So you start with a symplectic manifold and a separating hypersurface, which such that there is an S1 Hamiltonian action in the neighborhood of this hypersurface. So then one defines a symplectic cut as follows. You separate, you cut open the manifold along the separating hypersurface and then mod out the hypersurface by the S1 action, so that on both sides, this modded out quotient becomes a codimension 2 symplectic submanifold. And it's a result of Eugene Lerman that both X plus and X minus are smooth symplectic manifolds, and Y, which is the S1 quotient of the hypersurface, is a symplectic submanifold on both sides. So that's the definition of a symplectic cut. And this quotient, which the boundary modded out by S1, which we call Y, is a divisor. It's a codimension symplectic submanifold. So symplectic, and it's called a relative divisor. And the simplest example, the first example of symplectic cut is that of a point blow up, where in which case the separating hypersurface is a sphere around a point, so there's a boundary of a dartboard ball. And if you cut along the sphere and mod out by S1, one of your pieces is the point blow up, and the other piece is a copy of CPN. And the relative divisor is a CPN minus 1, which is S2n minus 1 modded out by S1. So if you were to draw, think of this as a toric blow up, that would be the picture in the moment polytope. Okay, so a natural generalization of the symplectic cut is a multiple cut, where the symplectic manifold X has a collection of hypersurfaces, and each of these hypersurfaces has an Hamiltonian S1 action in their neighborhoods. And on the intersections, the S1 actions fit in together to form a Hamiltonian torus action. So for example, schematically, an example can be represented as follows. So here, Z1, Z2, and Z3 are hypersurfaces with S1 Hamiltonian actions in the neighborhoods. And in the intersection, which is Z0, these S1s fit together to form a 2 torus Hamiltonian action. So that's the picture. And so each of the 3 S1s are different subgroups of the 2 torus. And if you perform the cut, which is a multiple cut in this case, so it's a standard thing. You disconnect along the hypersurfaces and mod out each of the hypersurface by the S1 actions. So as a result, what happens is on the corners, in this case, this Z0 is a corner, you end up quotienting by your T2. So you get 3 smooth symplectic manifolds. And the output of this cut operation, they are called cut spaces. And they also have relative divisors as before, but in this case, the relative divisors have normal crossings. So for example, in the piece X1, you have a Z1 mod S1 and Z2 mod S1 are relative divisors, and they have an intersection, which is Z0 mod T2. Questions so far about the setup? Okay. So the main question we are going to ask ourselves is, can counts of holomorphic curves, pseudo-holomorphic curves in the full manifold X, I call it an unbroken manifold, be expressed in terms of counts of holomorphic curves in the broken manifold? I haven't yet introduced a broken manifold. It will arise in a natural way from these cut spaces, which we just defined, but it will be defined very soon. And the second question we are going to ask ourselves is, can we do something more to say that these counts of holomorphic curves are just sums of products of curves in different pieces of the broken manifold? So the objects which we end up studying there are three different objects. Unbroken maps. These are just standard pseudo-holomorphic maps living in the symplectic manifold X, whose domain is a nodal curve. And then this next object is a broken map. Here also the domain is a nodal curve, but different components of the curve map to different components in the broken manifold. And there are matching conditions at nodes. And there is a combinatorial way. So this is going to be one of the take-home points of the talk. It's that these broken maps come with a combinatorial object, underlying combinatorial object called the tropical graph. And thirdly, the third object, which is going to answer the second question in the previous slide, is a variant, is called split map. It's a variant of the broken map in which the matching condition is somehow degenerated into a purely combinatorial condition. So when you're doing a curve count, there is no matching condition. So essentially you're taking products of curves in different pieces and taking sum over different types. So these questions which we asked 2 slides ago can be restated as follows. So can counts of holomorphic curves in the unbroken manifold, called unbroken maps, can they be expressed in terms of counts of holomorphic curves in the broken manifold, that is broken maps? And the second question is whether these objects are related to split maps. Okay, so these are the questions. And the talk is naturally divided into 2 parts where we go from unbroken to broken and broken to split. So let me start with the first question. So we talk about the first question in the context of a single cut, which is pretty much of symplectic field theory. So so I review this so that we can use it for the more complicated case of the multiple cut. So we want to somehow produce a cobordism of the moduli spaces of pseudo-holomorphic curves in X, omega to pseudo-holomorphic curves lying in the broken manifold. So in order to do that, we consider a family of almost complex structures called J nu, such that as nu grows larger, the neighborhood of the hypersurface looks like a longer and longer neck, and eventually we allow the neck length to go to infinity. And by a neck length, by neck, I mean that it's a fibration whose fibers are holomorphic cylinders of length nu, and nu is the parameter which is just going off to infinity. So the neighborhood of the hypersurface is called the neck region, and that just the J nu's are designed so that looks like a longer and longer neck. So an easy example, a way of visualizing this is the case of a sequence of conics degenerating to a pair of lines. So the neighborhood of the origin looks like a longer and longer cylinders, and eventually as the length of the cylinder goes to infinity, the lines just break into 2 lines. So that's roughly the kind of picture we have in mind. So in all this, we need to remember that the symplectic form is unchanged. The sequence of JNUs are all tamed by the symplectic form. So as a result, the moduli spaces of JNU holomorphic curves are homotopy equivalent for all nu. So the question we need to address is what happens in the limit as nu goes to infinity. And the theorem, this is the SFT theorem, SFT compactness. It basically says that if you have a sequence of pseudo-holomorphic maps with uniformly bounded area in the sequence of next stretched manifolds, then a subsequence converges to a broken map. So that's the SFT statement. And it's called holomorphic building, and that's what we are calling broken map, but there are minor differences. But holomorphic building is a good picture to have in mind if you've seen it before. Okay, so and just to review this quickly, so if you have a sequence of maps in next stretched manifolds, the limit looks something like this, which means that there are you get some limit components in x plus, some in x minus, and some sink into the neck. Or in other words, these components land in these pieces which are the hypersurface times r, which we call a neck piece because it was obtained by stretching the neck. So now we are finally in a position to define what a broken manifold is. So in case of a single cut, the broken manifold consists of x plus and x minus and the neck piece Z cross R compactified at minus and plus infinity. So Z cross R is called the neck piece. It is the compactification of Z cross R by adding divisors as at plus and minus infinity. And therefore it is a P1 bundle over the relative divisor. So in some sense, we like to think of it as a thickening of the divisor. So the divisor has 4 dimension too, so you thicken it by a P1 bundle, so the fibers have 2 dimensions. So broken map consists of components in x plus x minus and the neck piece. And these maps satisfy a matching condition at nodes. And what is a matching condition at nodes? It's that the evaluation of both sides of the nodal point is the same on the relative divisor, y. And the second condition is that the intersection, so y is a divisor, so there and it's holomorphic. So there is a positive intersection multiplicity with it has with the map at any nodal point. And we require that the intersection multiplicity is same on both sides. And intuitively, why do we get this matching condition? It's because nodes are formed by the convergence of long cylinders with small area. So since both sides are kind of coming out of the same cylinder, they asymptote to the same point on the relative divisor and have the same winding number around the relative divisor.
So Sushmita,
this is another picture to say the same fact, which is that if we have a sequence of cylinders whose lengths are going to infinity and they have a uniformly bounded puffer energy and small enough area, then these are all asymptotically close to, oh yes, there is a question. Yes, sir.
May I ask a question? So the broken curves that you obtain from SFT compactness, and that means that the hypersurfaces that you are considering are themselves from the start quantization bundles over symplectic manifolds. So the S1 action is free and they are contact hypersurfaces in such a way that the orbits of the S1 action are closed orbits of the red vector,
right.
Correct?
So Z is S1 fibered, so it's not contact. Yeah.
Okay.
Yeah, but it's a free action, yes.
Okay, good. Thanks.
Okay. So, yeah, so if we have this sequence of cylinders with small area, then they are asymptotically closed to a trivial cylinder, and a subsequence of these cylinders converges to a node with an intersection multiplicity. So, this picture is just kind of restating the same fact from the previous slide. So what happens in the larger picture is that if you have a converging sequence of maps and next-stretched manifolds, they basically have pockets of high area separated by long cylinders with very small area. And a pocket of high area converges modulo translation in the target space. So yeah, remember that the length of the neck goes to infinity. So we do need a translation in order to make these pockets of high area converge. And these translations, so for example, if you consider this pocket of area 5, there is a sequence of numbers, t sub 5 nu. And if you translate this pocket by that amount, so a subsequence will converge. And these numbers, t sub 5 nu, the sequence is called a translation sequence. So in the end, what we get is not just a map. So in addition, for each component in the limit map, we also have a relative position in the neck region. And that relative position is given by the translation sequence via this formula. So it's ti nu divided by nu as nu goes to infinity. So roughly speaking, for each of the components in the broken map, you get a position in the 0, 1 line segment. And wherein if the component converges in x plus or x minus, then it's going to land up in either 0 or 1. Otherwise, it's going to be somewhere in the middle in the line segment. So this map from the graph of the domain curve to the 0, 1 line segment is actually the tropical graph. It is not very meaningful in the case of a single cut, but it'll be highly relevant in what we are going to talk about next. So any questions so far? Okay. So let's look at a multiple cut. So this is the cut from our first, one of our earlier slides, the definition of a multiple cut. So
here.
Yes.
Sorry, we're trying to figure this out. Do you hear it?
Yes, I can hear you.
Okay, thank you. So just technical question. So this stretching in the stable Hamiltonian setting, is this was this considered in this old compactness paper? I don't remember. Or is this something you worked out?
No, this is from this is the standard aseptic compactness.
From the aseptic compactness paper. Okay.
Right. Like after this is the new stuff.
Okay. Thank you very much.
Okay. So a multiple cut. So this is a picture from the first slide, and so the kind of the data that defines the multiple cut is a polytopic decomposition of the dual of the algebra of the torus, which we just think of it as Rn for the rest of the talk. And so the polytopic decomposition is you have a collection of top dimensional polytopes, and you also label all their intersections and put it all together. And that's the set of polytopes, which they are Delzahn polytopes, which describe our multiple cut. So, yeah. And this is the example which we are going to kind of have in mind for the rest of the talk, which is the example of two orthogonal symplectic cuts. So the polytopic decomposition for this is is given in the figure, and it has 4 top dimensional polytopes. There in four other one-dimensional polytopes, which are the intersections, and one other polytope, which is just a single point right at the center. And when you actually perform the cut, you get these cut spaces, 4 cut spaces, and they have some relative, each of them has 2 relative divisors. Okay, so now we perform neck stretching in 2 directions instead of 1. In general, you know, the geometry of the cut is going to tell you how exactly to stretch the neck. But we'll work with this really simple example where it's easy to generalize from the single cut to the multiple cut. So it's just, there are two orthogonal neck directions and both are getting stretched. So there are some regions which are getting stretched in one direction, as in these gray regions, and the white region in the center is getting stretched in two directions. And the theorem here is again analogous to SFT compactness, which says that if you have a sequence of maps with bounded area, then a subsequence converges to a broken map. And similar results have been proved by other people, but you know, the terminology of the broken map, the tropical graph and all evolved gradually. So these are just various stages of the same thing. So let me talk a little bit about the convergence in case of a multiple cut. So the elements in a convergent sequence are roughly of this form, which is there are pockets of high energy separated by long cylinders with small area. And the target space is a broken manifold. And what's a broken manifold in this context? So remember that the polytopic decomposition was given by a collection of polytopes. So broken manifold is going to have one component or one manifold corresponding to each of those polytopes which occurred there. So therefore, in this picture of two orthogonal cuts, we are going to have 9 of these pieces which are part of the broken manifold. And what this is, it consists of the cut spaces, which are the 4 dark gray ones in the corner, and corresponding to each of the divisors, we have a P1 fibration of the divisor. So these are the light gray ones. And the center one, it's a P1 square fibration. So in general, each of the pieces of a broken manifold is a TP, is a toric fibration, and the dimension of the torus is exactly the codimension of the space XP. So the divisors are going to be P1 bundles, and the higher codimension submanifolds are going to be going to have higher dimension toric fibers. So the relative submanifolds and cut spaces are thickened into top dimensional pieces in the broken manifold. So that's the main point. So that's the target space of a broken map. And further, in the broken manifold, the various components have a natural action of a complex torus because they are all toric fibrations. And again, these cut spaces, since they weren't really thickened, they have the action of the torus on those is trivial. The light gray ones have a 1 torus acting on them, and the middle piece has a 2 torus acting on it. And the broken map, in addition to a collection of maps, it also consists of a tropical graph. And the tropical graph lives in something called a dual complex. So in this example of a single cut, we saw that the tropical graph lived on a line segment. Now we are stretching in 2 directions. So the natural guess for a dual complex should be just a product of 2 line segments. And indeed, this idea can be generalized to any polytopic decomposition. So the dual complex consists of a complementary dimensional polytope P cap for each polytope P in the polytopic decomposition. So the cut spaces just become points, and the center point, which was a point in the polytopic decomposition, is a 2-cell in this dual complex. So that's where the tropical graph lives. Okay, so finally, getting back to what a broken map is. A broken map consists of a domain nodal curve modeled on a graph. And for each component, you have a map to a component of the broken manifold. And these maps satisfy some magic conditions at nodal points, which I'll describe next. And they also, a broken map also consists of a tropical graph, which is a map from the graph underlying the curve to the dual complex. And the tropical graph is actually a combinatorial invariant of the map, because if two tropical graphs have the same edge slopes, we declare them to be isomorphic. So it's not something that deforms as you deform the curve. So going back to this picture of what a sequence of converging maps look like. So if you have a converging map, a sequence of converging maps of this form, then the limit is going to have that as the tropical graph, because these translation sequences keep track of the relative positions in the neck. And now the neck is two-dimensional. So each of those components is going to be assigned a point in the square, which is the dual complex. So it's kind of visual. Wherever this pocket of high energy lies, you get a point there in the dual complex. So, and additionally, an important property of the tropical graph is that to each nodal point, there is we know their intersection multiplicities with relative divisors, which are same on both sides. So at a node W, the intersection multiplicity with relative divisors W are equal, and that number, this mu1 comma mu2, gives the slope of the edge in that tropical graph. So right. So yeah, so basically the tropical graph has all the information about the intersection multiplicities. And so, you know, we can't just have a random set of components with whatever intersection multiplicities as a broken map. We should be able to embed that graph with those intersection multiplicities in the dual complex. So that kind of cuts down what a broken map can possibly be. And the reason why we have these you know, intersection multiplicities are integers. So these slopes necessarily have to be rational. Any questions so far? Okay.
So maybe I can ask a question. Sure. To make sure I understand correctly. So the tropical graph is not just combinatorial. I mean, in a sense, it's combinatorial, but it's related to the integral lattice there, because each slope gives you the intersection data with all the divisors.
Right, right, at the nodal point. So each edge represents a nodal point, and each nodal point has an intersection multiplicity data, and that's represented by the slope of the edge in the tropical graph.
I also had another question, like, why do you use the tropical terminology? Because I'm used to thinking of tropical objects as being some degenerations of under the logarithmic map of complex curves, you know, like tropical.
Yeah, actually,
curves.
it's kind of like that, because we have these cylindrical. If you look at this picture, for example, these are cylindrical things degenerating into a relative divisor, which is so.
Okay.
And they kind of reduce to a purely combinatorial data.
Okay.
Okay. So yeah, so this is what broken maps would look like. You know, if you have three components, two in neck pieces with, sorry, two in cut spaces and one in the middle neck piece, you could have a tropical graph like that. And then in the second example, U1 lies in the one-dimensional neck, so V1 lies on the edge. Let me say something about the matching condition in the case of a multiple cut. So as in the case of a single cut, the first condition is as expected, which is that if you project the nodal point to this manifold XP gap, which is the intersection of whatever divisors happen to pass through that point. So the projection to xp cap is equal on both sides of the node. But remember that earlier, above the node, we just had a C star bundle sitting, but now it could be a torus bundle. So there are many directions at the corner. So we are actually hitting, the node is hitting a corner, as you can see in the picture. So, so there is an additional vertical condition which says that the leading Taylor coefficients of U plus and U minus in the directions normal to the corner match up. So I'll state this in a different way in the next slide. So what's really happening is that at a node, both sides, on both sides of the node, the map is asymptotic to a trivial cylinder. And a trivial cylinder is essentially a one torus. And so which we call T mu C, and it's generated by the multiplicity vector. So the matching condition can be thought of as you mod out both neighborhoods of the nodes, you nodal ellipse, you mod out by this one torus, and then the evaluation maps will be the same. So, you know, if you're mapping to a corner, you're actually mapping in a region where there is a higher dimensional torus action, but you take the direction of the intersection multiplicity, mod out by the one torus, and then you have matching. So that's essentially what the matching condition is. So what this tells you is that in standard chromovitin theory, stable math theory, the matching condition has dimension of x. Whereas here, the codimension of the matching condition is dim x minus 2, because we are actually doing the matching on a quotient by a complex one torus. So, so the matching condition has dim x minus 2, which means that the presence of a node does not decrease the index of the map. So therefore, maps with nodes occur generically. They are not they don't occur in a smaller stratum. They occur generically. So just yeah. So for example, in case of a single cut, one piece in x plus and one piece in x minus, that occurs generically. But you'll see that in the multiple cut case, we can even have more complicated configurations that occur generically. Okay, so coming back to the torus actions. So you remember that the neck pieces had torus actions, and the cut spaces had a trivial torus action. So let's call this. So there is different tori acting on different pieces. So let's take a product of all of those and consider the subgroup which preserves the matching condition at the nodes. So preserving the matching condition means that if you have a node on both sides, the torus can only move the components in the direction of the trivial cylinder asymptotically close to the node. So remember that for a node, we had a trivial cylinder or a one torus, which kind of the node is asymptotic to that one torus. And in order to preserve the matching condition, the relative action across an edge E can only be in the direction of that trivial cylinder. So that's the condition which gives you the subgroup of the product of tori, which preserves the matching conditions. So this might seem kind of hard to understand, but the really nice thing is that the symmetry group can be read off from the tropical graph, because this matching condition just comes from the intersection multiplicities, which is completely encoded in the tropical graph. So the symmetries of the tropical graph are the infinitesimal generators of the tropical symmetry group. So, and by symmetry of the tropical graph, I mean the ways of moving the vertices in the tropical graph without changing the edge slope. So for example, in the graph in the left, you have no way of moving the vertices without changing the edge slope. So this tropical symmetry group is going to be finite. And in the second case, these two smaller dots can be moved to the dotted positions. So that's a one-dimensional degree of freedom. And it turns out that the tropical symmetry group is actually C star. So that one generator gives you a C star. So, so whether the amount of flexibility, symmetry the broken map has is completely encoded in the tropical graph. And why is this an important remark is that the action of the tropical symmetry group does not have infinitesimal stabilizers. And as a result, if you're looking for small index maps, they are going to be rigid. So a broken map of index 0 or 1 has a rigid tropical graph because if you have even a single infinitesimal generator, that's going to give you you need at least a two-dimensional moduli space. So therefore, if the index is 0 or 1, it's guaranteed that the tropical graph is going to be a rigid one. So let's go back to the case of a single cut which we understand well. In the case of a single cut, the only rigid tropical graphs are these line segments with vertices in 1 and 0. Because if you put a vertex in a neck piece in the middle of the line segment, then we are free to slide that vertex back and forth on the line segment. So therefore, if there are any components in neck pieces, then the broken map cannot be rigid in case of a single cut. So whereas in case of multiple cuts, components in neck pieces occur generically, as we saw in the previous slide. So using this theory, the curve count invariant which we deal with is the Fukaya algebra of a Lagrangian. So that's, I won't get into details of that. All I'll tell you is that there are these composition maps in the Fukaya algebra. The Fukaya algebra is an infinity algebra. And the composition maps are defined by counts of disks, holomorphic disks, whose boundary lies on the Lagrangian submanifold. And in our case, we assume that the Lagrangian is contained in one of the cut spaces and it's in the complement of the relative divisors. So when you do the cuts, it just stays put in one piece. It's not affected beyond that. So the theorem we prove is that there's a bijection between, roughly speaking, there is a bijection between holomorphic disks in the broken and unbroken manifolds. And the slightly finer statement is that for a fixed area bound, the broken maps are bijective to unbroken maps for a large enough neck length. So yeah, basically these are bijections for large neck lengths. So that involves the compactification theorem, which we saw earlier, and a reverse cloning theorem. And using this, one can define a Fukaya algebra in the broken manifold, and there is a Fukaya algebra in the unbroken manifold. Those two are homotopy equivalent. So one can do all the Fukaya algebra business completely in the unbroken world because we have this homotopy equivalence. Questions? Okay. So, but the thing is, this is kind of an aside, this slide, in that in our Fukaya algebra definitions, we are only interested in 0 and 1-dimensional moduli spaces. We are just not interested in anything beyond that. So in this paper, we didn't really work with higher dimensional moduli spaces. But if you are to ask me how these various strata fit together, this is what we expect, although we didn't prove it. It's that let's take the tropical equivalence classes of all the maps below a certain energy bound. Then they fit together into a compact orbifold. And in this orbifold, generic points have a finite tropical symmetry group. And for any tropical graph gamma, the moduli space of maps of type gamma form a stratum whose codimension is same as the dimension of the tropical symmetry group. So maps which have a large tropical symmetry group, after you quotient them out, they form a small stratum in the moduli space. So, but most of the maps are, these maps are going to have a rigid tropical graph. That's the generic situation. So like basically, if you look at a sequence of maps and you look at the compactification, then in the limit, the tropical graph will acquire more symmetry. And then when you mod out, it becomes a smaller stratum. Anyway. Okay, so finally, I move on to the last section of my talk, which is about how to go from broken maps to split maps. So first, I'll explain what our motivation is in doing this. So we are the single cut scenario. So recall that in a single cut, we had a matching condition at nodes for broken maps, which is that the evaluation of the lift of the node is same on both sides. So that's the matching condition. So as a result, if you were to write down the moduli space of broken maps, that's going to be the moduli space in X plus and the moduli space in X minus and a fibered product over Y, because both these moduli spaces have an evaluation map at the node, and we want those evaluations to be the same. So the total space is going to be a fibered product. Now our question is, can we do some homotopy so that this fibered product is changed to a product? And the idea is this deformation is carried out via a Morse flow. And this is following Bourgeois and Chris Woodward. And so the idea is as follows. Let's define a space of T-deformed token maps, wherein the matching condition is replaced by a T-deformed matching condition here. So, which means that instead of requiring both those evaluation maps to be the same point, we require that one of them is shifted by the time T flow of the gradient flow of a Morse function. So we choose a Morse function. It's part of the datum of the deformed map, and require that these two nodal lifts are connected by length T gradient flow segment. And so then it's easy to see that the moduli space of T-deformed maps is homotopy equivalent to the moduli space of broken maps, because we just did a homotopy. And then if we take a limit, those length T trajectories become infinite length trajectories, which are broken trajectories. So trajectories which are broken at a critical point of the Morse function. So therefore, so we call these new kind of maps an infinite deformed map. And here the matching condition is that the lifts of the two lifts of the node are connected by a broken flow line. And since we did this process through a homotopy, we have essentially proved that the moduli space of broken maps is homotopy equivalent to the moduli space of infinitely deformed broken maps. So what the upshot of this is that the moduli space of infinitely deformed maps is a sum of products, because on the one end, we can count maps which lie on the unstable, the node maps to the unstable locus of P, and the other side where the node maps to the stable locus of P. So these two moduli spaces can be thought of independent of each other, and we just take a product and we take a sum over all critical points. So, so that's what I mean by degenerating the matching condition to split form. And the basic idea which goes into this is that the diagonal in Y cross Y is homotopic to a union of products of stable and unstable manifolds. So that's basically what's happened here. So instead of requiring the the pair of evolution nodal points to map to the diagonal, we require them one side to map to the stable manifold and other side to map to a unstable manifold of a critical. So if we try to do the same thing in case of multiple cuts, that doesn't quite work because the unstable and stable manifolds might be contained in relative divisors. And as a result, we have components which collapse to relative divisors and form bubbles. So the nodes will actually be mapping to some other space. They won't even be in the same space where we have defined the Morse function. So the whole approach kind of fails. So, and in general, if we do this procedure, we are sure to create additional bubbles as time goes to infinity. So the previous procedure cannot be replicated. So now I'll set out to describe how we achieve the split form. So we make a few assumptions. We don't do this in full generality. We assume that the nodes lie on toric varieties and the torus invariant divisors are relative divisors. And the example to have in mind is that one of the cut spaces is a toric variety, so that automatically all the nodes map to its divisors or their intersections. So all of those are toric varieties. And the Lagrangian is a torus orbit in this space. Okay. So this is an even more particular example to have in mind. If the whole thing, the whole space is a toric variety and we have applied this multiple cut, and we'll be deforming the nodes which are coming out of the piece P naught. So to let X be a toric variety, so the neighborhoods of torus invariant divisors are separated using cuts. And there is one cut space XP naught, which is diffeomorphic to X, but with a smaller symplectic form. So all the torus invariant divisors of XP naught are relative divisors. So we'll do an example with this picture. So let me tell you how we degenerate. So the degeneration procedure is similar to what we just saw in the case of a single cut using a Morse function. So what we do is, originally we have at a node a matching condition of this form, wherein we quotient by one torus and do an evaluation. So we define a deformed map where instead of requiring both these sides to be equal, we shift one side by an element of the torus, which is called, this element is called a deformation parameter. So we are deforming the matching condition by a parameter tau. And actually this is same as the Morse condition. We can also think of this as a Morse deformation because you know, this tau will, if we were to do a Morse flow of the correct moment map, then this is same as the flowing by the gradient flow of the Morse function. So these we are doing roughly the same thing as what we did before, except that we are using the toric structure much more here. Earlier, we didn't require a toric structure at all. Okay, so what we did there was we increased the deformation parameter to infinity. So we do the same thing here. So we consider a sequence of deformation parameters and let them approach infinity. And if you have a sequence of tau nu deformed maps, we examine their limit. So we require a small additional condition in that we require the deformations to happen in a generic direction. So we require that, so we take a generic element of the Lie algebra of the torus and require move to infinity in that generic direction. If we do that, then we claim that the sequence of deformed maps converges to a split map, which we now define. So what is a split map? It's a kind of a broken map, but with no matching condition at nodes. This is exactly what we wanted. We wanted to get rid of the matching condition. But in return, the additional dimensions, they show up in the form of an addition of a higher tropical symmetry group. And the reason we have a higher tropical symmetry group is that we acquire more freedom. So the tropical symmetry group is constrained by the fact that how the components across a node can be moved. So if you drop a condition, matching condition at one of the nodes, we acquire more freedom, more in how the torus can act on the components. Yeah, so the last, so the direction of deformation is also part of the datum of the split. So some intuition, some more intuition behind this, the deformation process is as follows. It's that suppose you're on a toric variety and you start with a point and move the point in the direction, in a generic direction. So eta is the algebra element, which is generic, and we act by eta on this point y. Then the limit is going to take you to a fixed point of the torus action, right? So that's roughly what's happening here. We are deforming the matching condition in a generic direction, and it's taking us to some kind of a fixed point. And so it's kind of counterintuitive, but in our modelized space, those smaller strata actually correspond to larger tropical symmetry group. So we need to get a full tropical symmetry group in order to say that we have actually reached a fixed point. And for that, we need the genericity for deformation direction. And in the end, the theorem we prove is that the modular space of split disk modulo the action of the tropical symmetry group is homotopy equivalent to the modular space of broken disk. So this is what we would have liked. So we prove the homotopy equivalence. And so we can use, instead of the broken maps, we can use split maps to define the Fukaya algebra. And that's a new kind of Fukaya algebra, which we call the tropical Fukaya algebra. And it turns out that that's homotopy equivalent to all the previous versions of Fukaya algebras. So let me show you this example. So, so we start with this toric variety where we cut out the neighborhoods of all the divisors. So if you look at a Maslow index 2 disk, in the broken picture, it's going to consist of a Maslow index 2 disk in B0 and a sphere in the smaller pieces. So this is a Maslow index 2 broken disk. So remember that this small piece which contains a sphere, it's actually a P1 fibration. So one of the P1s is going to match up with the disk. So that gives us a broken disk. Now, if we deform the matching condition by tau, what we end up doing is we end up shifting the sphere by a distance of tau. So tau is an element of the complex torus. So this is the tau deformed map. And if we allow tau to go to infinity, the sequence of tau nu deformed maps converges to a split disk, and the split disk is of this form. So the small sphere moved. So what happens is that the small sphere moves and collapses into a divisor. And whenever something collapses into a divisor, it actually moves into a neck piece. So we get the sphere in the neck piece. And in the neck piece, there is a C-star action. And that exactly accounts for what we said earlier, which is that you produce extra dimensions by getting rid of the matching condition. So in this case, the matching condition is of codimension 2. So that reappears as the tropical symmetry group, which is a C-star in this case. And on the other hand, the broken maps also come with the tropical graph. So what happens to the tropical graph is that earlier, this red dot would have been on the P1 hat, but now it moves on to this edge. So it's free to move in one direction. So we have produced a one-dimensional freedom in the tropical graph, which exactly is the C-star tropical symmetry group. So, so yeah, essentially, the broken map here is in bijection to a C-star orbit here. So that's kind of the correspondence between the Burton and the split pictures. And as you can see that there is no more matching condition here. So I was going to talk a little bit more about how to say that, you know, how the freedom in the tropical graph again gives us the additional tropical symmetry. But maybe I'll skip that and just say that, yeah, I'll just end with this theorem, which is that we use this split version of the Fukaya algebra to prove, rather reprove the Fu theorem, the Fukaya and collaborators theorem, where they show that a Lagrangian torus is unobstructed. So we can prove that using the machinery of split disks. So, so the proof uses the tropical Fukaya algebra, which is homotopy equivalent to the broken Fukaya algebra. And in a split map, the moduli space of the disk part is invariant under the action of the compact torus. And that straight away gives the unobstructedness for the Lagrangian. So, you know, a lot of the challenge in proving unobstructedness comes from there is sphere bubbling, and then you no longer have a T invariant moduli space. And we kind of get over that fact by this kind of decoupling the matching condition so that the disks themselves are the T invariant. So that's so that gives us a proof of this unobstructedness. So that's an application of this technology, and hopefully there are more. So I'll stop here.
Thank you very much. So are there questions?
Yeah, we have a question here.
Okay.
Hi, Sushmita. Georgios here from HP. So, if I understand correctly, so you can take a toric manifold, and then you can kind of cut out the toric divisor by.
Right. Right. Yeah, that's how we prove this Fukaya theorem.
Because if you remove the torus inside the kind of, you cut it out and remove this. The central piece is just a piece of the co-channel bundle, then. This in this picture, at least.
The central piece is what? Sorry.
It's just a part of the co-channel bundle of the torus, right?
Yeah, I mean, you can just think of it as a C star n, right? Like then.
Just this.
Yeah, that's right. It's yeah, you could say it's a potential bundle. Yeah.
So do you have any formulas then for, because the outside then it's just should be related to some kind of Gromov-Witten invariant of the original manifold with some conditions. It feels like this could be used to prove some result that Dmitry Tonkonog has announced.
Okay.
The potential on the Lagrangian torus, which is counting disks on the torus, then of course, and you get these disks, and then Gromov-Witten invariants in the ambient manifold with incidence conditions.
Because so what's the ambient manifold you're talking about?
Because if you remove the central piece, what is rest is just closed curves.
No, actually, that's not quite right, because I removed the central piece, but the sides are also they are P1 fibrations or torus fibrations, so they are not just curves.
Yes, but there are no boundary conditions there, are there? The boundary condition is just seen in this.
Yes, the boundary conditions is entirely in the center. That's right. Yes.
The outside, if you forget about the central piece, then maybe you can consider it as some kind of a closed curve with some tangential conditions of different types, maybe.
Yeah, maybe. Yeah, maybe we could talk about it, but yeah, I think I'm not understanding what exactly you have in mind.
Okay, I'm insecure, but maybe you should look at that if it's relevant.
Yeah.
Thanks. Interesting.
So maybe I had a question. Your initial example, like maybe or even of simple cut, was a blow up. So what you describe is a way to go. Let's say you do a blow up, right? Then in the original manifold is now broken in two pieces. One is the blow up, and the other one is Pn.
Right.
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 And does it allow you to compute? I mean, in a way, the way you presented your result was somehow you have complicated object, and then you maybe break it into simpler pieces, right? But for the case of a blow up, it looks like you could use it so that you get information of what, say, the Fukaya algebra is in the blow up from the Fukaya algebra before the blow up, kind of reading the correspondence backwards.
Yes, that can indeed be done. Yeah, actually, we've worked on it in another paper, like in particular the case of the blow up, to kind of go from one side to the other. We can indeed do that. Yes, that's correct. Yeah.
Okay.
Yeah, and we can do it in larger like blow ups of submanifolds, although we didn't really work on that. But all those kinds of things are all possible with just a single cut.
Okay. And then I had another question, maybe related to connections to the literature. Is there an algebraic version of the construction that you are performing here?
The broken maps, yes. So the Brett Parker papers do that. But the split ones,
yeah,
I'm not.
But he's doing like, I mean, I don't really know his papers, but he's working with pseudo-holomorphic curves. I was rather thinking of whether people on the algebraic geometry side are able to perform constructions that you like the one that you are describing.
Yeah, I think there are constructions, but they are a little different because they consider degenerations instead of neck stretching. So they look similar, like even Gross, Siebert, Abramovich, and all these people. They're somewhat similar, but they are a little different because the next stretching are different from what they do.
Okay. Other questions? Well, if not, we can thank Sushmita again for a beautiful talk.